Welcome back to Algorithms and Uncertainty. Today we'll start to slowly transition to the third part of this class, which will be about online learning. In online learning, the setting is roughly speaking as follows. We have multiple time steps. In each of these time steps, we may choose one action, but unfortunately in advance we do not know how good these actions are. And the nice thing is now that we can observe over time how good they are, and this way we can learn what actions are the good ones and which actions are the not so good ones. And depending on this, we will have to adapt our choice for the future. We will be seeing multiple models in which actually an adversary defines the input, defines the sequence, defines the actions. But today we will be talking about a problem which is much more similar to the Markov decision processes that we've talked about so far, namely that we will have rewards which are drawn from probability distributions. There are no states, so all that we'll have to talk about is which of the actions do we want to choose in which step, because they each give us a random reward. Let's see how we can model this more formally. So this problem will also be called stochastic multi-armed bandits. Like also we are talking about other multi-armed bandits problems in this class. Here now we have n arms, or an arm we could also call an action, and we'll have capital T time steps. And in each step we may choose one action, which means here to pull one of these arms. So this is something like a slot machine. We'll have now n different options to choose from, and in each step we may choose exactly one of them. So let's call capital IT the choice in step T. And what we now say is that when arm I is pulled, we get a reward which is drawn from some di. So this di, this is a probability distribution which is supported on 0, 1, and it is unknown in advance. So this is now really crucial, because otherwise this problem wouldn't make any sense at all. Because what is it that we're now getting? So let's say RT, this is the reward of the algorithm in step T, and RT will be somewhere between 0 and 1, and RT is of course now drawn from distribution D subscript IT, This depends on which action we choose in step T. And what is it that we're trying to maximize? We're trying to maximize the expected reward over all time steps, summed over all time steps. So take the sum of all RT and take the expectation of these. Now, what would you do if you knew these probability distributions in advance? So if this was not true, that the distributions are unknown in advance, well, to maximize this quantity here, all you would do is you would just always draw from that distribution which gives you the highest of these rewards in expectation. So if we now say mu I is the expected reward from di, then we would optimally choose always I star such that mu I star is equal to the maximum of these mu I. But unfortunately, of course, we do not know these mu I. If we knew them, then everything would be simple. We would just choose always I star. So what can we do? This is exactly the question that we want to answer. We want to now try out arms in a smart way so that although we do not know in advance what the probability distributions are like, we will now want to choose arms so as to still get as much reward as possible. Our point of comparison will be this I star, which is just the best choice that we could make if we knew the probability distributions. And now we'll say that the expected regret of an algorithm is the following. Take the difference of what an optimal choice would be. If you knew the probability distributions, then your expected reward would be what you get from capital T draws from this I star, and from this subtract your expected reward. And our goal is now to design algorithms for which this regret, this expected regret, is small. We'll also see other notions of regret later in this class, but today we'll only talk about this kind of a setting where everything is defined by probability distributions. So all we actually want to do is now figure out which is the best arm to draw from. And for this we'll see two different algorithms. We'll first start with a very simple algorithm which just tries out each arm a couple of times and then decides, okay, which was the best arm so far. And then we'll improve this algorithm to get a much better guarantee in terms of the regret, because it is able to identify really bad arms earlier enough so that it does not pull them too often when it already realized that this is actually a bad arm. Let's now talk about a very simple algorithm for our problem, which is an explore-exploit algorithm. What do you mean by explore? Well, first we'll just pull every arm a couple of times, say k times, and then we hope to have a pretty good understanding of whether an arm is good or bad, at least if k is large enough. And then in the second phase, we'll just keep exploiting, meaning that we'll just pull the arm which turned out to be the best one in the explore phase. And this way we hope to make a somewhat good choice. So let's see what this will look like more formally. We have the exploration phase, where we pull each arm k times, and then we should compute the empirical averages mu I hat for every arm. And then in the exploitation phase, we will pull only the arm with the highest mu I hat. So this exploration phase will have k times n steps, and this exploitation phase will have t minus k times n steps. And I should mention that we assume that the number of arms is smaller or even much smaller than the number of time steps that we have. So how would you want to choose k here? You might, for example, draw only once from each arm. Well, this probably doesn't feel good because maybe this turns out to be a probability distribution where only 1 in 100 times you get a reward of 1, as opposed to some other probability distributions where you always get something, but less than 0.01. So this is, therefore you might want to choose k large enough. But if you choose k too large, then your exploration phase becomes too short. And then you get too few time steps remaining where you can actually exploit that you found out which of the arms is good. So you clearly have here a trade-off between the length of the exploration and the exploitation phase. The longer the exploration phase is, the better you know whether your arms, the arm which turned out to be good on average so far is actually a good arm, but the less time actually remains. And what we can show now is the following. If we set k to be t over n to the power of 2/3, this algorithm guarantees that the regret, what was the regret? This was the difference between what you would achieve if you knew the distributions and what the algorithm achieves in expectation. This we can bound by O of n to the power of 1/3 times t to the power of 2/3 times ln n times t. How can we prove such a theorem? Well, what we'll have to show is that if we choose k this large, then the empirical averages that we're getting here are nicely concentrated around the means, which means that we are very unlikely to keep pulling a bad arm in this exploitation phase. And to show this, to show that we have this nice concentration, we'll use two tools from probability theory without any proof. Namely, we'll use Hoeffding's inequality and the union bound. How are they defined? Hoeffding's inequality is the following. We'll now let Z1 through Z capital N be independent random variables. Such that AI is at most Zi is at most Bi with probability 1. And we now let Z bar be the average of the draws from Z1 through the N. Then we have for all gamma, which are non-negative, at the probability that difference of Z bar and its expectation is at least gamma. This is at most 2 times e to the power of minus n squared gamma squared divided by the sum of the Bi minus Ai squared. So the way you can understand this lemma is that it is just a quantitative version of the law of large numbers. So you can think of Z1 through Zn to be like, for example, the outcome of independent coin tosses. Let's say now you flip some coin n times, then these would also be identically distributed. This is nothing that we are requiring here. And now I mean Zi would be 1 if you see heads, it would be 0 if you see tails. And now the question is, what's the average of these Zi's? So which fraction of your coin tosses did you see heads? And the expectation of this average would of course then be the probability that you see heads. And what we're saying here is that, well, this now converges to the empirical average that we see here converges to its expectation. So we have here the empirical average, here we have its expectation, and that they differ by more than gamma, this probability is small. And what do I mean by this? Well, usually these Bi will be 1, the Ai will be 0. Then here we have we're dividing by n here. And then this will be something like n times gamma squared that we're seeing here. So the larger n gets, the smaller this probability will become. We'll see this in action in a bit when we're analyzing our algorithm. The other tool that we'll be using is the union bound. Namely that for any not necessarily disjoint events, E1, E2, and so on, we have that the probability that one of these takes place is at most the sum of these probabilities. So if these were disjoint events, then you would have equality here, but now they do not have to be disjoint, so this is why we're saying that this is only used as an upper bound here. Now if you know these two lemmas, then actually proving that our explore-exploit algorithm has this performance is actually quite easy. How does this work? Well, what does this tell us? Maybe let's go back to see what notation we used. Here, mu I had, this was the empirical average of k draws from the arm I. And now we can use Hoeffding's inequality to bound the probability that they are far apart. Namely, by Hoeffding's inequality, we now get that the probability that mu I hat and mu I are at least gamma apart, this will be at most 2 times, let me see whether I can fit this in here, yes, e to the minus 2 times what's capital N? Capital N was the number of draws that we have here. This is, in this case, k, because we're drawing k times from that distribution. Gamma squared divided by, and now what was BA and AI? BI was the upper bound, AI was the lower bound, and all rewards are always between 0 and 1 here. So this is why we'll have k times 1 minus 0 squared in the denominator. So this is nothing but 2 times e to the power of minus 2 times k times gamma squared. And now we can apply the union bound. What's the probability that there is an I for which mu I hat and mu I are at least gamma apart? This is nothing but the sum, or at most the sum of the individual probabilities. Note that here we're saying, okay, we have a union, but this is actually nothing but saying that there is one event that is taking place. So what's the sum of the individual probabilities of the events? Well, we have a bound for each of them, so we'll now have n times that probability. Good. Now what will happen? What will now happen in our exploitation phase? In our exploitation phase, we'll choose the arm with the highest mu I hat. And the question is, how big is the mu I hat of the arm for which, how big is the mu I for which the mu I hat was largest? And if we have that mu I hat minus mu I is less than gamma for all I, then this means that then for the arm I pulled in the exploitation phase, we have the following. We have, of course, that mu I hat is at least mu I star hat, because this is the arm that we're choosing, and this is at least as good as the best arm. But what else do we know? We also know that this mu I hat is not too far from the actual mu I. Namely, the actual mu I will be at least mu I hat minus gamma by this, and mu I hat is at least mu I star hat. And now we see, okay, this is also at least mu I star minus 2 gamma, because also mu I star hat is close to mu I star. So this tells us that if this is taking place, then we are actually pulling an arm which is not too bad. So this gives us that the expectation of our reward, of the sum of our rewards, this is at least how much? This is at least the probability that for all I, mu I hat minus mu I is less than gamma, times, and then we get just only consider our exploitation phase, that we have t minus n times k time steps, and for each of these steps we get mu I star minus 2 gamma. And how big is this probability? Well, this is exactly 1 minus this probability. If we now define epsilon to be 2n times e to the power of minus 2 times k times gamma squared, then this probability here will be at least 1 minus epsilon times t minus n times k times mu I star minus 2 gamma. So this is using this precise definition. And how big is this here? Well, this is 1 minus epsilon times t times mu I star minus n times k times mu I star minus 2 gamma times t plus 2 gamma times n times k. So let's simply ignore this last part. Then we have that this is at least 1 minus epsilon times t times mu I star minus n times k times mu I star minus 2 gamma times t. And this is now at least t times mu I star minus n times k times mu I star minus 2 gamma times t minus epsilon times t times mu I star. Actually, we could now add again epsilon times these things, but let's ignore them. This is only going in the right direction. So what does this now tell us for our expected regret? What was the regret the regret was t times mu I star minus the expected reward of our algorithm. So this will be at most n times k times mu I star plus 2 gamma times t plus epsilon times t times mu I star. And if you now set, and how does this all come together? Well, this is our definition of epsilon. Let's see that we now have by this that gamma is nothing but the square root of 1 over 2k times ln of 2n over epsilon. So let's plug this in here. We'll have n times k times mu I star plus 2 times this fancy square root term. And if we now choose k to be t over n to the power of 2/3 and epsilon as n over t to the power of 1/3, then this just works out. This will just be not too big. This will be in the order of n to the 2/3 times t to the n to the 1/3 times t to the 2/3 times ln n over t. You'll just now have to see that each of these terms is bounded by this much, okay? Now use that the mu I star is at most 1, and then this here you can upper bound by 1. You'll have n times k. N times k is exactly n to the 1/3 times t to the 2/3. You have epsilon times t. Epsilon times t is nothing but n to the 1/3 times t to the 2/3. And you'll also have this term here, and this is also in this upper bounded by this much. It's actually even something a little stronger. So maybe you could even get a slightly better bound here. But generally, what you will always get is this n to the 1/3 and t to the 2/3. I don't want to spend too much time talking about now the individual details of these calculations because they are not super meaningful here. What I'd like to put our attention on is these first steps, because there we showed, okay, with pretty good probability, the arm that we'll keep playing will be a reasonably good arm. And then you just have to do these messy calculations. I'm still trying to figure out if there is a nicer, easier way around them. Don't be distracted by this part. What you want to really understand is this first part, that you get a reasonably good concentration within the first k steps if k is chosen large enough. Now, what could you ask? Is there a better algorithm? Is there an algorithm which gives you a significantly better guarantee than this n to the 1/3 times t to the 2/3? And yes, there is. What we'll now get to know is an algorithm for which this gets down to square root n times t. Recall that t is actually much bigger than n. So this is what we really care about. And then I hope also the calculations get a little nicer. What can a better algorithm for our problem look like? So far, we were just trying out each arm a couple of times, k times, and then we decided to choose the best of these arms for good. The UCB1 algorithm that we now get to know is smarter than this. How can we be smarter? If an arm turns out to be bad, and by bad I mean really bad, then we probably just should not choose this arm at all anymore. And then we should actually learn this early in the exploration that, okay, these are good arms, maybe this, we have to explore a little more which of these arms is a good arm, and those arms, they're bad. We shouldn't actually use these arms anymore. This is the general idea. Unfortunately enough, the algorithm now turns out to be extremely simple because we're not splitting our sequence into an exploration and an exploitation phase, but we will do this all at the same time. And how are we doing this? We will keep a confidence bound for each arm for which we say, okay, the expected reward of a draw from this arm will be somewhere in this interval. And then what we're doing is we are at all times optimistic. We will keep drawing from the arm which turns out to have been the most promising so far. So UCB stands for upper confidence bound, and this is what the algorithm looks like. We first draw So first what we'll do is in steps 1 through n, we'll pull each arm once. And then what is actually important is that what happens in a step t, which is bigger than n. We let then mu I hat superscript t be the empirical average of all draws of arm I, and we let QIT be the number of times that arm I has been pulled. And in both cases, I mean before step t. Of course, because we're now saying what is happening in step t. Of course, now we have at least one draw from each distribution, so this is actually well defined what we're doing here. And now we let index I superscript t be defined as follows. Take the empirical average and add to this the square root of ln t divided by qi superscript t. And what we'll now do is we'll pull the arm with the highest index. And this is just what we'll keep doing. Why does this algorithm make any sense? Okay, these first things I think make total sense. Or maybe let's first start with this. This I hope is a no-brainer that we just pull each arm once, so that we have at least some idea of what's going on. Although this is not crucial, this could also be interpreted as a part of this, but let's not bother about this right now. Now, let's let we have a number of times which an arm has been pulled. And now what would we like to do? We would like to pull the most promising arm, maybe. And what we now see is, well, we could draw from the arm, we could pull the arm for which the empirical average has been highest so far. But this is not what we're doing. We're giving an advantage to the arms for which we have fewer draws, for which this QI is smaller. And for some reason which is maybe not super clear right now, which will turn out to be that you can see something that you will be able to see in the analysis, we'll choose this term to be exactly this big, square root of ln t divided by QIT. This is something like an upper bound on the standard deviation. So in the light of the uncertainty, we are now optimistic. We now think, okay, from this arm we have maybe if we have now a couple of arms for which we have the same empirical average, then we draw from that for which we have the smallest number of draws, which we've pulled the smallest number of times, because this is the most promising one. For this it is, well, somewhat most likely that this actually has the highest reward. Or at least we'll get to know something. We'll get more valuable information for this arm because we know we have fewer samples. We have less information about this arm than about the others. So this is where this index here is coming from. Uncertainty in the light of, optimism in the face of uncertainty. Cool. And now this algorithm is actually pretty simple, yet it does give us a better regret guarantee than the simple explore-exploit algorithm. What it will give us is the following. We'll be able to show that the expected regret of UCB1 is at most h times square root n times t times ln n plus 4 times n. So this guarantee, I hope you now realize, is better than the one that we previously showed, where t was to the power of 2/3. Now t is we're taking only the square root of t. Well, there with the previous bound we were taking n only to the 1/3. Now we're taking the square root, so this is actually higher. But as n is smaller than t, this is actually a better guarantee. Good. How can we prove such a bound? How will we prove this? What we'll do is that we will show that bad arms are just unlikely to be pulled very often. Because if an arm, or the worse an arm is, the more likely it is that it will have a bad index at a certain time, and then we will decide not to pull it anymore. This is the important lemma that we will be showing. Namely, for any arm I, we let Qi be the number of times that an arm is played overall. Now the probability that Qi is bigger than Si is at most 4 over T, where Si is equal to 4 times ln T divided by delta I squared, and delta I is equal to mu I star minus mu I. So what does this tell us? Well, let's now consider a very bad arm. For this delta I is big because this is how much is the best arm better than this arm. Then this means that this Si here will be small. And the probability that this arm is played more than Si times is small. For the best arm, for example, delta I will be 0, so Si just will be infinite. So this is actually not any reasonable bound. But that's okay. So the best arm we may choose as often as we like. The point of this lemma should be that we choose a bad arm only so often before we realize, okay, actually there should be a better arm out there. Before we prove this lemma, let's first see that this is actually all we need. How do we then prove our theorem? We let xit be 1 if the algorithm chooses to play arm I in step T and 0 otherwise. And now we also say that yit is a is the reward that the algorithm would get from playing arm I in step T. Why do I say that the algorithm would get? Well, this depends on whether it actually chooses to play this arm or not. We now also define a reward for all arms that the algorithm does not choose. Now, how big is the expectation of xit times yit? Well, the algorithm doesn't know whether or not this is a good reward or a bad reward. It just doesn't know which reward to get from this arm, because this is a random outcome. It doesn't observe until it pulls the arm. So we get that the expectation of xit times yit is exactly the expectation, the product of the two expectations. So it is the expectation of xit times mu I. And this now lets us rewrite the expected reward of our algorithm. The expected reward of our algorithm is nothing but the expectation of the sum of all these xit and yit. Now by linearity of expectation we can say, okay, take instead the sum over all xit times mu I. And this is now falling. Let's swap the sums here. We have here the sum of the xit, and then all of this gets multiplied with mu I. How big is this? This is the expectation of the sum of the xit. And what's the sum of the xit? Xit is 1 if the algorithm chooses to play arm I in step t. So this is nothing but the number of times that the arm is played overall, something that we now called qi. So this here is nothing but the sum of all expectations of the qi times mu I. And here now we suddenly realize that actually it matters how often an arm is being played. So we have now rewritten this in terms of the expected number of times that an arm is played. And we can even go further with this. We can now say that, okay, what's our regret? Our regret is t times mu I star minus this expected reward we might as well write this as follows. Take the sum, the expectation of the sum of the qi times mu I star minus, well, let's use this formula that we have for the second part. And why is this true? Well, this here is nothing but capital T, because this is just summing up for all arms how often it is played. So in each step we choose exactly one arm. And now we are getting to the following. We are getting to the sum of all expectations of the qi times mu I star minus mu I. For this we also have a letter, namely this is what we called delta I. So let's take a breath here and see what this is telling us. We now have rewritten our regret, namely as take the sum over all arms 1 through n, take the expectation of how often it is pulled, this arm, and multiply this by how far is this arm from being the best arm. So delta I hope you remember, was exactly this difference. How much better is the best arm than this arm? And now we can actually use this lemma to upper bound this expectation. By this lemma, the probability that qi is bigger than si is at most 4 over t. And this tells us that the expectation of qi is at most si plus the probability that qi is bigger than si times t, because qi cannot be bigger than t. So this is at most Si plus 4. And now this tells us that if delta I is at least delta, small delta, which are now defined to be square root of ln t over t, which I want to call a bad arm, then we'll have that the expectation of qi times delta I is how much? Now we need the definition of this Si. How big is Si? Si is this much. It is 4 times ln t divided by delta I squared. So this will be at most 4 times ln t divided by delta I plus 4 delta I. This was just plugging in the definition of Si. And now this is no more than 4 times ln t divided by small delta plus 4, because every delta I is at most 1. And now let's plug in the definition of delta. This is equal to 4 times square root of t times ln t divided by n plus 4. And what does this tell us for our regret? Our regret, for which we have precisely this, which we rewrote to be exactly this quantity. Now this we can split up into the parts where we have a good arm. Good arm means that we'll have at most, that the capital delta is at most small delta, and then we have the bad arms, for which things might be worse. But now we can say, okay, here we have that this is at most 4 times square root t times ln t divided by 4 by n plus 4. And here we have something similar, namely we can simply plug in our delta. And now overall we get that this first part here, this is nothing but at most t times delta, because again those sum up to at most t. So this will be square root n times ln t. The second thing here, square root of n times t times ln t. And this second here, what does this sum up to? This sums up to at most 4 times square root n times t times ln t plus 4 times n. And overall, so we get that this here is at most 5 times square root n times t times ln t plus for n, which I realize is in the constant even better than what we claimed before because I wasn't careful enough. Cool. So this is a little messy, but it's not super complicated. What we do is we rewrite the expected reward that we're getting in terms of the expectation of the respective qi times the ui. Now we realize, okay, this lets us also rewrite the regret. And now the only thing that we'll have to do is we'll have to see, okay, this expectation of the qi. This is small for arms which make this which have a large contribution to the sum, or for which the delta I is large. So either the delta I is small, then we're good, or delta I is large, but then the expectation of the qi is small. And this is exactly what is happening down here. It's just a little messy because you have to distinguish cases, but eventually you end up with exactly the guarantee that you want. So all we have to do now is to show this lemma here, that it is unlikely that a bad arm is pulled very often. We now want to show that this lemma holds, which means that if an arm is bad, then it is very unlikely that it is played very often. How do we do this? We will now show that actually the empirical averages that we're using in our algorithm are close to the true means. And this tells us that these at some point in the sequence, when we've pulled an arm often enough, that then suddenly it is less likely, or we will not play this arm anymore, but instead we would choose the optimal arm. And this gives us immediately an upper bound on how often we pull this arm. But before we get there, let's first show the following key property. Namely, that for all I, we have the following: the probability that there exists a t for which the empirical average that we have by this time minus the true mean is at least ln t divided by qit. This is happening with probability at most 2 over t. So what does this mean? This means that with only a small probability there exists a time step t at which mu I t is far away from mu I. And how do we define far? Well, this is something I hope that looks familiar to you, because this was exactly the thing that we added to mu I t to define the index. So we now say, okay, the probability that the two are apart, that there is a time at which the two are very far apart, far defined this way, is small. And it gets, of course, smaller the more samples that we've seen. How do we prove this? Well, what we'd actually like to do is just apply the Hafting's inequality and then see, okay, everything is nicely concentrated. All these mu I hats, they are nicely concentrated. But the annoying thing is, here on the right-hand side, we have this mu I t, which depends on how, or this is a random variable. And so also this mu I hat, this is not just a fixed number, the average of a fixed number of draws, but it is the average of, well, a random number of draws. But to deal with this, it is actually easier to think about this as follows. If we now draw t times from every distribution, and now what we can do is we can just play what the algorithm is doing from based on only these draws. So we, in advance, we now draw from each of the distributions capital T times, and now let's just see what the algorithm is doing. And now we don't need any further randomness because what we feed to the algorithm is just this sequence. And now we say that xi prime comma j, this is the outcome of the jth draw of arm I prime. Which now means that mu I hat at time t minus mu I is at least the square root t of ln t divided by qit for some t. This is, for this it is necessary that the average of the first j draws that we have from xi deviates from mu I by at least square root of ln t over k. So what we're doing here is actually just drawing k times from the distribution and say, okay, these will be our k first draws from this for this arm, and what is the average that we're seeing from this. And if we now have this for that this is, or let me rather start here, if this is not fulfilled at any time, then we'll certainly also have that this is not fulfilled for some k, namely for the k which is exactly the qit that we have here in our denominator. At the same time, this k might take strange values like capital T or so, which would mean that we were drawing capital T times from this arm, which will actually never happen in our algorithm. So what we're bounding here, this is actually a probability that is something that we do not actually see. But what we can now do is we can say, okay, what's the probability that actually this event here is taking place? For this, we can luckily just apply again Hoeffding's inequality. And we'll get that this is at most 2 over t squared. So here this was Hoeffding. And now this tells us that the probability that there exists a t for which mu I t minus hat minus mu I is at least the square root of ln t divided by qit. This is nothing but at most the probability that there exists a k for which we have that the average of the first k draws from that distribution minus mu I is at least square root of ln t over k. And now this is something that we are able to bound, namely this is at most t times 2 times 2 over t squared, which is nothing but 2 over t. And here this step was using a union bound. Good. And so this completes the proof of this lemma. This lemma is saying that the probability that there exists a t for which the two are apart, namely the empirical average and the mu I are far apart, the probability that this ever happens is small, whereas far we define it based on how often we pulled this arm so far. Now what does this tell us? This tells us that for all I, we have that the probability that there exists a t for which the index is at most mu I is at most 2 over t. Where is this coming from? This is coming from exactly this here. Recall that the index we're getting when we're adding exactly mu I t hat and this much, so that this index will ever be smaller than mu I, this would mean that also this event is taking place. And analogously, we can also say that the probability that there exists a t for which the index is bigger than mu I plus 2 times the square root of ln t divided by qit, this is also small. So the index will always be at least mu I and at most mu I plus something. This is how you should read this expression. And now finally we can prove our key lemma. If qi is bigger than si, what has to happen? There has to be some t0 such that qi at t0 is exactly equal to si, so there has to be time at which the arm has been pulled already si times, and the index of this arm is at least the index of the optimal arm, because we are now playing this arm and not any other arm, in particular the optimal arm. But the probability that there exists a t at which the index of I star is at most mu I star. This is small. And also the probability that there exists a t at which the index of I is at least mu I plus 2 times square root of ln t divided by qit, this is also small. But what would have to happen at this time t0 when we are choosing this arm I rather than I star? Well, what would have to happen is that one of these two things goes wrong. Namely, if neither of these two events happen, what do we have? We have that for all t, the index of I star is bigger than mu I star, and the index of I is smaller than mu I plus 2 times the square root of ln t divided by qit. So in particular, at time t0, what would have to happen there? We would have we'll have that index I star is bigger than mu I star, and the index of I will be less than mu I plus, and now the thing is, we know the value of qi at this time. This is Si. And how big is Si? Let's go back to the lemma. The lemma was stating Si, setting Si to be this much. And this is not a coincidence, because now this here, by the definition of Si, this here will be exactly delta I. So this is saying that this is mu I plus delta I, which is nothing but mu I star. And so this is now a contradiction, because now it doesn't happen that the index of I star is bigger than mu I star, and at the same time the index of I is less than mu I star, and the index of I is bigger than the index of I star. So this is a contradiction to I being pulled another time. So overall we get that the probability that Qi is bigger than Si, this is at most the probability that there exists a time t at which one of these things here fail. So either we'll need this, or we'll need the other part. And for this, we can bound the probability just by a union bound by 2 times 2 over t, which is 4 over t. Good. So, unfortunately, it is pretty ugly to write this out really formally. So the point is that the intuition, I think, isn't too difficult, that we at all times the index is somewhere between mu I and mu I plus the square root of ln t divided by qit. And now what we'll have to have is that for there to be more than SI steps at which we choose this arm, there has to be this has to be violated at some point, because otherwise we would at some point choose a different arm than mu I, than this arm I, because at this point the index, otherwise if this is fulfilled at all times, then the index is actually pretty good. Yes, so as I was saying, this is a little complicated to flesh out formally, because here I'm still struggling to make this an easy, straightforward argument, but to me this still feels a little weird, a little, yes, how do I say this? Because I haven't found a way around proving this as a contradiction, and because this is not happening for sure, but only with a certain probability. And the reason why this feels so, to me, complicated is because this is not happening, this is only happening with high enough probability, but if this is not, or it is necessary for our bad event to take place, that one of these events does not take place. Good, so now we've seen the UCB1 algorithm, and we've already also analyzed it. We've seen a regret bound of square root n times square root t times square root ln t. This is also almost optimal. You can get this down to square root n square root t with a different algorithm, which is a little smarter, but generally this is about what you actually need for this problem. You could, in principle, also get a guarantee which depends on these deltas, on these delta I, which is actually only in the proof of our theorem. You would have to stop at some point, and then things actually become even easier to give you a bound on the a regret bound which depends on the deltas. But I thought also in comparison to the easy explore-exploit algorithm, it would be helpful to have a guarantee which only depends on n and t. In the next lectures, we'll turn to a similar but different problem in which we assume that these rewards or costs then are not drawn from probability distributions, but they're rather defined by an adversary. There we'll have to apply different techniques, although the general spirit of the kind of guarantees that we'll be achieving will be quite similar, namely that we'll also get some regret bounds, which we will then again see as square root t, square root n times square root t, and so on. Until then, I hope you stay safe. Please do let me know if you have any questions. Bye.